previous video, we talked about directional derivatives, and we also talked about the concept of the derivative of a function from Rn to Rm. So let's state a theorem that connects those two concepts. So the theorem is, let U be a subset of Rn, and let f be a function from U to Rm. If f is differentiable, at A, so let's say that U is an open set in Rn. If f is differentiable at the point A, which is an element of U, then all directional derivatives of f at A exist, and the directional derivative f prime at A in the direction U equals the derivative evaluated at A times the vector U. Okay, so let's just recall that df of A is the matrix that represents the linear transformation that's defined when the function f is differentiable. And so this is an m by n matrix, right? And U is a vector in Rn, so we represent that as an n by 1 matrix, right? A column vector. And the product is an n by 1 matrix, so a vector in Rm. And that makes sense because the directional derivative is a vector in Rm. Okay? So let's prove this statement. So for notational convenience, let B be this matrix df of A, and set, so here we're letting U be an element in Rn. Okay. Set H equal to Tu in the definition of differentiability. Well, since f is differentiable, this tells us that f of A plus Tu minus f of A minus B times Tu over the magnitude of Tu approaches 0 vector as t goes to 0, right? Now let's evaluate the limit as t goes to 0 from the right. If t goes from 0 to the right, okay, so we have the limit as t goes to 0 from the right of f of A plus Tu minus f of A minus B times Tu over, well, the bottom, it just becomes t times the magnitude of U, right? So this is equal to 0. Now multiply both sides by the absolute value, by the, what is it called? The magnitude of U. Right. this limit, I mean, one way to see what's going on is we can just, this absolute value, absolute value, magnitude of u is just a constant, right? So we can just move that out of the limit, and so, yeah, I mean, we don't even need to multiply by the absolute value of u. We see that this, the limit of, let me just erase, this limit must be approaching the 0 vector, right? And this limit, okay, this is the limit as t goes to 0 from the right of f of a plus tu minus f of a over t, and then minus, so this t times u, here in this product we can move the t out, and so when you just split up the fraction, this is going to be this minus b times u is 0 vector, and that's the same as saying that the limit as t goes from 0 to the right of f of a plus tu minus f of a over t approaches b times u. Sorry, the limit equals b times u. Which is exactly, right, df of a times u. And this limit is equal to the derivative. Sorry, this limit is the directional derivative. So the notation I used was f prime of a u. Okay? So that proves the statement in the case where t is approaching 0 from the right. Now if you're approaching 0 from the left, then you just do the same thing. Just by moving, right, so if you have the limit as t goes from 0 to the left, we know that this minus b times tu all over t times the magnitude of u. So the magnitude of t times u is the 0 vector, and that implies, so if t is approaching 0 from the left, then near 0 t is negative, and so this guy factors as the absolute value of t times the magnitude of u, and then this is going to be negative t times the magnitude of u, and then you just move negative magnitude of u out, and so this tells you that the limit as t goes to 0 of f of a plus tu minus f of a minus b times tu over t is the 0 vector, right? And you just do the same reasoning. You just by the same steps as we did before, we conclude that that this is true. Right. I mean, more precisely, okay, maybe I was a bit sloppy here. Once you get that this limit from the right is b times u, and once you show that this limit from the left is b times u, right? When you put that together, when you put these two statements together, those two statements, so let's call this one 1 and 2, 1 and 2 together imply that the two-sided limit exists. So you know, I'm being a bit sloppy. I mean, technically, if I wanted to be super precise, what I should say is that this limit here exists and equals b times u, and the limit here exists and equals b times u. Therefore, the two-sided limit exists and equals b times u, which is df of a times u, which is what we wanted to show. So that completes the proof. Okay, now this is something that we'll use later, but notice that it doesn't really help us say what the directional derivative is, because we still don't have a theorem that explains what exactly this matrix is. But we'll actually use this theorem to prove that the matrix is something familiar. Okay. And so the theorem says that if you know that f is differentiable, then all the directional derivatives exist, and it's equal to what you get when you multiply this matrix by the vector u. And we still don't know what this matrix is. And so this theorem by itself has limited use. However, okay, let's just focus on the statement that if f is differentiable at a, then all directional derivatives exist. Let me try this one more time. Is it true that if all directional derivatives exist, then f is differentiable? Well, the answer is no. So note that if you have, if all directional derivatives of f at a exist, f might not be differentiable, need not be differentiable at a. Okay, so to justify that, I should give an example. So let's look at this function f from R2 to R, which is defined to be f of xy is equal to x squared y over x to the fourth plus y squared if xy is not 0, 0, and is equal to 0 if xy equals 0, 0. Okay, the first claim is that all directional derivatives of f at 0, 0 exist. That's the first claim. Well, so okay, let's prove that. So let's say that you have a vector u which is not equal to 0 vector, right? And this is an R2. Let's write the vector u as hk, so at least one of h and k is non-zero. then f, so the directional derivative, if it exists, is going to be the limit of a certain term. So let's take a look at that term. It's f of 0 vector plus tu minus f of 0 vector over t. And this is equal to f of tu, so that's f of tk minus f of the 0 vector, which is by definition 0 over t. And this is equal to, by definition of f, t squared h squared times tk over t to the 4th power h to the 4th power plus t squared k squared all over t. And this is going to be t cubed times h squared k over t to the 5th h to the 4th plus t cubed k squared. And if you factor out a t cubed, which you can because t is non-zero, this is h squared k over t squared h to the 4th power plus k squared. And so the directional derivative does exist. So f prime of the 0 vector in the direction u equals, well, let t approach 0, right? If t approaches 0, then you get h squared k over k squared. So that's h squared over k. If I guess you want k to not be 0, right? If k is not 0, so you don't get 0 on the bottom. If k is 0, then, well, this thing is just 0, right? So the limit as t goes to 0 will just be 0. And that shows that this in fact does exist, right? The directional derivative exists for all u. Okay, so this exists for all non-zero u. Now I have to prove that this function is not differentiable at the point 0, 0. Okay, let's prove that. First of all, let's say that you have a function g from R2 to R that is differentiable at 0, 0. Well then, what can you say about the derivative, dg evaluated at 0? This must be a 1 by 2 matrix, right? With real entries, so dg of 0 is some matrix, say A comma B, and since now we're applying the theorem above that the directional derivative g prime of the 0 vector in the direction u is equal to dg of the 0 vector times u. And if u is hk, then this is just going to be the number ah plus bk. Right? So what we showed is that whenever you have a differentiable function from R2 to R at 0, the directional derivative in the direction u has to be a constant times h plus another constant times k. And that is not what we have. Right? I mean, just look at this. This is not a constant times h plus a constant times k. So since f prime of u 0 does not have this form, f is not differentiable at the point 0, 0. Okay, so let's just summarize what we did in this video. We proved that if you have a differentiable function, then the directional derivative is given by taking this matrix df of A and multiplying it by the vector u. In particular, all the directional derivatives of f at A exist. But we also showed the converse is not true, that if all the directional derivatives of f exist, then f might not be differentiable. And so, the condition of differentiability that we gave is stronger than just the directional derivatives existing. Right? Because we gave an example of this function which is not differentiable, but all the directional derivatives exist. So somehow the definition of differentiable we gave, we need more than just the directional derivatives exist. Right? The directional derivatives have to exist in order for the function to be differentiable, but that's not enough to guarantee differentiability. Okay, that's all for this video. In future videos, we're going to use this theorem to prove, to show what this derivative matrix actually is. And it will be in terms of something called the partial derivatives, which is a type of directional derivative. Okay, thanks for watching.